maybe a little less. All right, so we are now in Chapter 2, which is on curves and frames. And to start with, in Section 2.1, I just give you this like laundry list of important mathematical general terms, you know, and in particular, the way we describe distance, we have a few different ways we do it in mathematics, all right? So the first of all is if you have like a set paired with a distance function. So the distance function is, it takes in pairs of things and it outputs a number from 0 to infinity. So this is distance function. And it has to be symmetric. It has to have distinct points are at non-trivial distance, like distance from P to Q equals 0 if and only if P equals to Q. It's non-negative. Symmetric was the distance from P to Q is equal to the distance from Q to P. And 4, it has the triangle inequality. The distance from P to R is less than or equal to the distance from P to Q plus the distance from Q to R. Triangle inequality. All right. Now, this definition, you know, a set paired with a distance function, this makes the pair S comma D a metric space. So a metric space is just a set with a distance function. Now this is not quite the definition I have in section 2.1. Uh-oh, sorry.
It's nice to Q, nice to the plus the distance function of Q.
That's an R with a smudge. Okay, so now, example, if we take S equal to R3, with the distance from P to Q equal to what? You know, P1 minus Q1 squared, P2 minus Q2 squared, P3 minus Q3 squared. That defines a distance function, and that's our usual distance function, right? That's the Euclidean distance. So R3 paired with the usual Euclidean distance between points is an example, the quintessential example perhaps, of a metric space. I mean, some people would say, really, well, what's the most boring metric space possible? Maybe this, S equal to the reals with the distance from A to B equal to what? Square root of, square root of A minus B squared, right? If A and B are just real numbers, what is that I just wrote, though? I'm being a little bit silly. That's not usually the formula we write for the distance. I mean, if I give you a number line, and I say, here's A, here's B, what's the distance between them? What do you tell me? B minus A, yeah, okay. You're like, you're weird, you should put B minus A. Fine, I can do that. I can do that. But this is actually what? This is the absolute value of B minus A. So this is really the natural generalization of absolute value. It's the same formula even, with just additional squared terms added. Okay, anyway. So if we have a metric space, we can talk about open and closed sets in terms of open and closed balls. Well, in terms of open balls. So definition, B epsilon of P is equal to x in the space such that the distance from x to P is less than epsilon. So this is an epsilon ball in metric space S. If you look at an open ball, an epsilon ball in R3, what is an epsilon ball in R3? It is literally a fuzzy ball, right? It's a ball without the edge. What's an epsilon ball in R? So we go P plus epsilon, P minus epsilon. That's an open ball in R1 is just an open interval, like that. A open ball in R2 is actually an open disk of radius epsilon. In R3, it is literally an open ball, just like it sounds like. In R4, I can't draw a picture, except sarcastically. So, and I've already made that joke in here, so I won't do it again. All right? So, definition, for U, a subset of S, a metric space S, all right, is open if for each P in U, there exists epsilon greater than 0 such that the ball of radius epsilon centered at P is a subset of U. This thing I just wrote down for P, what that says is that P is a interior point of the set U. So a set is open if every point in the set is an interior point. So for example, open balls are open sets. Every point inside an open ball is an interior point, right? Do you see why that is? You pick me, here example. Suppose this is the open ball we're looking at, right? You pick me any point in there. Let's say Q, right? Can you find an epsilon that keeps it within the ball? Suppose that the radius of the ball is R for the sake of discussion. What would you choose as epsilon to keep it within the ball? I mean, pictorially, you just be like, well, put it right there, right? So if we could do proof by picture, we'd be done. And I'm actually content with that at a certain level in here. Depending on where the point is, right. So let's see here. The question is whether or not that point is closer to the middle or to the edge, right? So maybe we should do something like epsilon equals the minimum of R over 2 or the distance from P to Q. Maybe that would work, I feel like that would work for a careful proof. You could show that epsilon gives you a ball of radius epsilon centered around Q, which is a subset of the ball of radius R centered at P. Okay, so I'm going to move on here. How do we define a closed set? So anyway, that's how we define an open set in Rn. An open set in Rn is one for which if you take a point in the set and you take a little open ball around the set, it's within the set again. If you can do that each point within the set, it's said to be open. All right? And what's a closed set? Well, V, a subset of the set S, is closed if and only if V, if and only if S minus V is open. So closed sets are defined to be the ones whose complements are open. I mean, that seems a little odd at start, right? But check this out, for example. Take the closed disk in R2. Closed disk, right? Like this. So x squared plus y squared less than or equal to 1. That is a closed set in R2. Because its complement is open. How do I know its complement is open? What's the complement of this in R2? I'll draw it over here separately. The complement is what? I make it dotted, right? It's all this stuff out here, right? It's x squared plus y squared greater than 1. That's the complement. Pick any point you like outside the unit disk, right? And I say it's geometrically evident, obvious if you will, that there is a little open ball centered around there, which is still outside the closed disk and hence inside the complement. This shows that the closed disk is in fact a closed set, which is good because we call it a closed disk, right? So if you called the closed disk a closed disk and it wasn't actually a closed set, that would be very bad terminology, right? I mean, this happens in mathematics every so often, right? But fortunately not here. Open sets, open intervals are in fact open. Closed intervals are in fact closed with respect to the usual metric space structure on the reals. All right? All right, so that's metric space in a nutshell. Notice that so far I have said 0 about any kind of additive structure, right? I didn't talk about vector addition here at all. All of the addition has been done for the values of the distance function. So next up, let me just tell you briefly what an inner product space is. What is an inner product space? Definition. A vector space, V, with map, let's say, usually we oftentimes use angle bracket. I'll use angle brackets for it, for notation. From V cross V into the reals is an inner product space. If you have a couple axioms for this inner product, number one, the inner product is bilinear. By that I mean if you got cx plus y comma z, you can pull it out. Cxz plus yz. And likewise, if you have cy plus z in the next component, you can pull the c out. So it's bilinear, meaning it's linear in both slots. It's symmetric. Symmetric, meaning that xy is equal to yx. for all x and y in the vector space. It's bilinear, symmetric, what else? And it's positive definite. 3. Xx is greater than or equal to 0, and xx equal to 0 if and only if x equal to 0. So a vector space paired with an inner product is called an inner product space. Can you guys tell me any examples of inner product spaces? So how about R3 with the inner product of two vectors, x and y, equal to what? How about the dot product, x dot y? Here I'm using x and y as vectors, right? If it makes you feel better, I can put vectors on everything. Vector, 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 vector. Don't feel obligated to write them if you don't want to. So in fact, yes, that's an inner product. Is that the only inner product on R3? I mean, you can define other ones. Here's a silly one. Just put a 2 in front of the first thing. It still satisfies all the axioms, and yet it's not the dot product. There's lots of other modifications you could make. So that's an inner product space. A more exotic example would be this. While we're here, if you take the set of n by n matrices, you can define an inner product of two matrices, A and B, as the trace of AB transpose. Do you know what the trace of a matrix is? It's the sum of the numbers on the diagonal of the matrix. So it just adds together the diagonals of the matrix. This formula is nothing more than a slick formula for like A11, B11, plus A12, B12, plus dot, 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 plus ANN, BNN. This is like a super sneaky, tricky formula for if you just took the matrices and strung them out in a super long vector. It turns out that this is equal to that, yeah. Not just the diagonal, it's through all possible indices. I mean, it's actually the sum over all I and j of Aij, Bij, if you want a more honest formula.
So would it be AT2, BT2?
Yeah, it's got, listen. It will be more productive for me to actually write out what this works like. So you do 1 times 5, plus 2 times 6, plus 3 times 7, plus 4 times 8. That is literally the dot product of these two matrices. Well, I say dot product, but I should say inner product. But the set of n by n matrices with respect to this inner product is a well-known construction. This, anyway, okay, enough. All right, so what else can we say? Well, next up, last but not least, you can talk about a normed linear space, or NLS as they're sometimes called. A normed linear space is a vector space V with norm, which is a mapping from V to, well, I suppose 0 to infinity again. Now, norm, we should think of intuitively as being vector length. All right? So a norm linear space is a vector space with a definition of vector length. And so, like, it has to satisfy the norm of, well, let me try to keep my numbering the same as my notes. It's positive definite. The norm of x is greater than or equal to 0 for all x in the vector space. 2. What happened to my plan of not writing all this out? The norm of cx is equal to the absolute value of c times the norm of x. So this is for all c in the reals and for all x in the vector space. 3. What else do we have? Triangle inequality, of course. So the length of the sum of two vectors is less than or equal to the sum of the lengths of said vectors. That's the triangle inequality. So there's a triangle inequality both for a metric, for a distance function in a metric space, and also for the definition of a norm. They're different, but related. And that's it. So can you tell me an example of a normed linear space? So example, if we take R3 and we say that the norm of a vector v is what? How about the square root of v dot v? Ever seen this? To calculate the length of a vector, we can take the square root of the dot product of the vector with itself. This is Calc 3. And that's just a sneaky way of writing the formula. v1 squared plus v2 squared plus v3 squared. So there's a theorem that I should mention here while we're at it. Theorem V with inner product V, inner product space, then V with norm given by norm x equals square root of inner product x with x is a NLS. So any inner product space can also be looked at as a normed linear space because you can always use the inner product to define a vector length. And this we do in Calculus 3, right? Now here's where it gets tricky. You can ask the question, what about the converse of this theorem? Is it possible to take a normed linear space and convert it into an inner product space? And there the answer is usually. But there exist examples where it's not possible. I think I've said more than enough for here on that. One last, so if you haven't figured out yet what I'm doing, this part of the course is really for breadth, right? Have you guys heard this stuff in other courses? Who's had real analysis? Did you talk about metric space in real analysis, yeah? Right. But you didn't talk, of course you probably didn't talk about inner product space in real analysis, right? Probably not. You probably didn't talk about normed linear space in real analysis either. But I hope you can kind of appreciate that these ideas are connected, right? I mean, all three of these things I've talked about, they're all trying to get at that same central idea of how do we describe distance, right? Should we describe distance with the length of vectors? Because we can use vectors, displacement vectors, to connect points, right? So if you had a norm linear space, you can make it into a metric space by using the distance between 2 points to be the length of the displacement vector. So like the distance from P to Q is the length of the vector that goes from P to Q, which we usually would do Q minus P, right? That's true, but very good. Distance is not always in a straight line. So this context, right? So the context here is in a vector space. So in a vector space, we have lines between all points. So we just use the distance between straight lines if we're talking about this concept of distance. Fair enough. But again, metric space is a more general notion because it doesn't assume vector space. You can take a subset of a metric space and it's still a metric space. You can't just take a subset of a linear space, a vector space, and necessarily have a vector space, right? It has to satisfy the subspace test. And that's a pretty strict condition. There's lots of subsets of a vector space, which are not themselves vector spaces, right? Take a half plane. Is it a vector space? Well, no. If you take any vector in the upper half plane, multiply by -1, you're in the lower half plane. So it's outside the set. It doesn't satisfy that closure under scalar multiplication. One last thing. Have you guys ever heard of a Banach space? No? All right, well, a Banach space is a complete normed linear space. You say, well, what does complete mean? This you should have talked about in real analysis, for those of you who had real analysis. What did we know about a Cauchy sequence of real numbers? What does it do? Cauchy implies what? A Cauchy sequence is a divergent sequence or convergent? Cauchy sequences are convergent sequences. In fact, in a Banach space, that's a biconditional. In any metric space, it is always the case that convergent implies Cauchy. What Cauchy means is that if you go far enough out in the sequence, you can make the distance between points beyond that point in the sequence as close together as you want. Like, if you go far enough out in the tail of a sequence, you can make difference between 2 points in the tail as small as you want. This is Cauchy. Convergent, of course, is a little bit different than that. And you can get Cauchy implies convergent in what's called a complete space. Real numbers are complete. All right. This set of matrices, n by n matrices, with respect to this norm, I didn't tell you what the norm was. What would the norm? What I mean this norm? So we could use that. This is the so-called induced norm. Induced norm. It's the norm which is built from the inner product. So the induced norm in this example, like the length of a matrix, if you wanted to talk about that, it would be the square root of the trace of AA transpose. And so a set of n by n matrices with respect to this notion of distance, of length, in fact, if you take a sequence of Cauchy if you take a sequence of matrices, which is Cauchy, it is in fact convergent. So this is a complete space with respect to this notion of norm. There are lots and lots of spaces which are complete. If you ask me for an example of a space which is not complete, the only thing I'll ever probably tell you is the rational numbers. Rational numbers form a metric space. I mean, rational numbers form a normed linear space. Like the sum of two rational numbers is linear, excuse me, if you add two rational numbers together, do you get a rational number? Yeah. And, oh, see, now I'm getting into somewhat theoretical linear algebra. My apologies, but a rational multiple, if you take a rational multiple of a rational number, it's again rational. So like rational numbers are a vector space over the rational numbers. But in any event, if you take a Cauchy sequence of rational numbers, it doesn't have to converge to a rational number. For example, the digits in the square root of 2, these converge to the square root of 2. The square root of 2 is not rational, right? You proved this in your proof course. It was also on the test, right? No? I'm just guessing. It would probably be on my test if I was to teach the proof course. It's a good, silly problem. But. All right, anyway. One last bit I always try to say whenever I'm giving this spiel is about what is a circle. See, if we have a metric space, we can talk about a circle, right? What would a circle be in a metric space if you want to give a definition? Circle centered at P with radius R is set of points such that what? And I'm going to limit the discussion here, centered at P. I'm going to say circle in R2 paired with some distance function, okay? Otherwise, I'm not going to be defining a circle. I'll be defining like a sphere or something else. But let's say R2 with a distance function. It's a set of points such that the distance from P to x, y, right, is equal to R. So if your distance function is the usual Euclidean distance function, what do you get? So let's say the distance from P to Q equal to square root of P1 minus Q1 squared plus P2 minus Q2 squared. Then, well, if you set that equal to R, what do you get? You get the usual circle, right? So this gives usual circle. All of a sudden, why do I got it? Yeah, okay, P. So usual circle. But you could also use the following as a distance function. Let me call it D1 PQ. You could use the absolute value of P1 minus Q1 plus the absolute value of P2 minus Q2. That actually also defines a distance function. Just take the sum of the absolute values. So let me put P equal to 0 to make things easier, and just for my sake of my artistry. So P equal to 0. It looks like that, right? It turns out that if you work through this, this one here. So if you take the distance from 0 to the xy, this would become absolute value of x plus absolute value of y. And so you're setting that equal to 1, let's say. Let's look at radius 1 for the sake of discussion. What is the solution set of absolute value of x plus absolute value of y equal to 1? You only do fractions? There's 4 non-fraction answers, here, 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 and here. But you're also right that there's half-half, right? Half-half, that's a good point. And there's that one, and that one, and that one. And if you connect the dots, that gives it to you. So the circle, with respect to the one distance, this is also sometimes called the taxicab distance, because it's basically saying the distance between 2 points, you have to sum the horizontal distance plus the vertical distance. It's sometimes called the quote-unquote taxicab metric. So with respect to the taxicab metric, the circle's a diamond. Something cool happens if you do like the distance, let's say d3, the cube root of the absolute value of p1 minus q1 cubed plus the absolute value of p2 minus q2 cubed. This is also a distance function. And if you study the unit circle in that case, it ends up looking like somebody took the circle and blowed it out, but fixed these, it still has these points fixed. But this time it's kind of like a little bit more out like this. I should have made this bigger, my bad. I should be actually looking at the board I'm writing on. Good night. You guys gotta help me. And if you keep going, there's something called the soup. You can say d infinity if you like. D infinity PQ. It's the max of the absolute value of p1 minus q1, comma absolute value of p1 minus p2 minus q2. In that, if you set that equal to 1, it gives you, it just keeps, it's the square. So it's not wrong to say every one of those shapes is a circle. The one I started with is the Euclidean circle, right? The diamond is the taxicab circle. That black square, that's the infinity. I don't know what the name of that is for here, but the when you do this for a norm, it's called the soup norm or something like that. But anyway, I shut up. So that's a pretty good place to stop again. And we'll start again at